In this video, we're going to talk about concave mirrors and the mirror equation. So here's my concave mirror with a principal axis, so I can draw some objects and focal points. For this example, I'm going to say the focal point is right about here, and the focal length is the focal point F. And the focal length, I'm going to write up here, is going to be, for this example, 3 centimeters. And we're going to place an object right about, let's say right about here, at a distance DO. Again, these distances are all measured relative to the mirror itself. So I'm going to put an object here. It's going to be an arrow, and that's going to be DO. I'm going to say is 5 centimeters away from the mirror. Okay, and the object here is to do two things. First of all, to draw the ray diagram. So we can locate ray diagram to find the image. And B, we're going to find DI quantitatively using the mirror equation. So let's do the first one, the ray diagram. So to draw a ray diagram, recall, we're going to draw two rays. We just need two rays to locate where the image is going to be. So let's say a light ray comes down from the ceiling or from the sky, hits the tip of this, and one particular one will be reflected off of the tip and be parallel to the principal axis. And we know that light rays that are parallel to the principal axis, or parallel to the mirror here, will go through the focal point, because that's a definition of what the focal point is. I'm going to draw that line all the way down here. So it reflects, it goes all the way down like this. We also know that there's another light ray that will go and hit this point right there, and it'll come in at an angle of incidence relative to this principal axis and reflect off at the same angle. So I'll try to guesstimate where that angle is, right about there. And we can see those two light rays meet right about there, and they meet at a point below the principal axis, meaning that the image we're going to see is inverted. It's upside down. So that's where DI is qualitatively. It's an upside down image, and if you were to put a screen right there, you'd see that image upside down. So how do we find that location quantitatively? So we're going to use the mirror equation, 1 over F. Now emphasize, we're going to draw right number 1 here, number 2 is on my template, and number 3 solve. I want to see that those numbers there. 1 over focal length is equal to 1 over DI plus 1 over DO. Again, you don't need to memorize these are on the equation sheet, but you should know what these mean and where they're measured from on an actual mirror. Step 2, list variables. So we have the focal length F, we have DI, and we have DO. So let's list the variables here. So the focal length was given. It's a number of 3 centimeters. Make sure we put our units in here. 3 centimeters. Image we do not know, so I'm going to put a box right there. We do not know what the image distance is, although I have an idea of where it's going to be. And the object distance we know is 5 centimeters. So I do know that number because that was given above right there. So the solve part, I break it in a couple different steps to make sure we can understand where these come from. So I got 1 over F is equal to 1 over DI plus 1 over DO. You can hear that motorcycle in the background there. Step 2, I'm going to plug in 1 over 3, because the focal length is 3, equals 1 over DI, which I'm trying to find, plus 1 over DO, and DO is 5. Okay, so I have an algebraic equation with one variable. So the next step, I'm going to do some division, just break it up in smaller steps here. So this is going to be 0.33 is equal to 1 over DI plus 0.2. So 1/5 is 0.2. The fourth step is I'm going to solve for DI, or in this case 1 over DI. 1 over DI is equal to 0.33. Now note, I'm going to bring this term to the other side of the equation, so it's going to be minus 0.2 minus, which gives me 0.13. And the last sub-step is DI is equal to, because I'm going to cross multiply. 1 over di is 0.133, so di is 1 over 0.13. And if you do the math there, you'll get an answer of 7.5. And because everything was in centimeters, it's going to be in centimeters. Brackets around the units, box your answer. And you can see in the diagram here, that kind of makes some sense because this is 3 and 5 relative to the mirror here. That's about 7.5. In order to draw this to scale with a ruler and straight lines, you could actually predict this location relatively accurately, both quantitative and qualitatively, using the array diagram and using the equation. So those are the steps for drawing array diagrams and solving quantitatively. List the equation, list variables, and solve. I break it up into 5 sub-steps. For the array diagram, we have one array that's parallel to the principal axis. It goes to the focal point. Another one goes through, hits the mirror right here, and comes back at the same angle. And there's actually a third, if you like. You can also draw this. You know that one light ray that goes, I'll just a dotted line here, goes to the focal point. It's got to be parallel to the principal axis, and if you trace this, you see that that one also meets right there, and that's where the object's in focus. If you were to put a screen right there, you'd see that you'd form an image. So those are ray diagrams and the mirror equation for a concave mirror.